everyone. So this video is the second of the Stack and Queue videos, and in this video, we're going to talk about Stack implementation using a linked list. Now, to get started, if you're going to implement a stack using a linked list, you should hopefully already have a linked list already created. Now, you actually do have this in a combination of your Lab 3 and your Lab 4. If you took the iterator code out of Lab 4 and added it to Lab 3, or you took the push and pop functions out of Lab 3 and put it into Lab 4, you basically will have a something that you can use to implement a stack. But you want both the iterator code as well as the Lab 3, as well as all the push and pop functions for the queue and stack combined, okay? So let's take a look at the stack implementation first. So imagine taking all the code from Lab 3, putting it together with all the code in Lab 4, and then put all of that into some list that you call linked list.h. I'm not going to do that. You're going to have to do this for yourself. Okay, but imagine that you have done this. Now, what this means is that you will now have access to the following functions: push front, push back, pop front, pop back, begin, cbegin, and cend iterator operators, which are dereference, plus plus, minus minus, not equals, and equals, and of course two versions of plus plus and minus minus. Now, give me a quick second. Okay, that doesn't work because I did that. Okay. There we go. Okay, so I wanted the list sort of on the side here as I write my functions. So there we go. So this is a list of the things that we can use: push, pop, begin, end, iterators, and so on. And what we want to do now is we want to start implementing this linked list. So how do we go about doing it? So first of all, remember that we already have a linked list written. So choose one of your linked lists, either Sentinel or non-Sentinel. And since you've implemented them both, it really doesn't matter which one you use, because other than the declaration, the code will be the same. So I'm going to actually use dlist t and call this data member the stack. So what does this do? Well, this creates an instance of the linked list as a data member. And so this object has a linked list in it. Okay, now you can actually implement this using inheritance, where a stack is derived from one of the linked lists. But if you do that, you have to do private inheritance so that people cannot access the push and pop functions of the base class, the list class, directly. So I find that this implementation I generally like better. So we'll do it this way. Okay, so here we have this right here. Now, the constructor for the stack actually doesn't have to do anything, because this object, when it's created, is created without arguments, right? It's an empty list to begin with, so that's all we're doing here. Now for push. So how are we going to write push? We're going to take a value and put it into the list. And there are really two options that we can choose from, either push front or push back. Which one should we choose? Now, since this is a doubly linked list, the choices really, the push choice doesn't have as big an effect. And I'll tell you, we'll talk about why this is and draw some pictures in a moment. But I can actually choose either one. If this was a singly linked list, though, I would only be able to do a push front, okay? And we'll talk about why that is in a moment. So let's start with this idea of doing push front. So if I wanted to push a value into the list, I can start with just simply taking the stack and doing push front with the data. Now this takes the data, puts it into the front of the linked list, right? So how then do I write pop? What would pop look like? Which of the two pops would I write? Does it still not matter, right? And it turns out that the choice that you make for your pop function is actually dependent on the choice that you made for your push function. Because at the end of the day, remember that the stack is a first in, last out data structure. If you had chosen push back, over here, you have to pop back. If you choose push front, you have to pop front. They have to match, okay? So in the case of a stack, because I chose push front, my option for taking data, for removing data, is to use pop front. Okay, I can't actually do it with pop back anymore because I already chose push front. Now, why is that? Why do I say that you can't, after you've chosen what to do for push, you don't have a choice for pop? The reason for this is as follows. So imagine that I called push 2 times, push 5, push push 10, push 9. Okay, or 3 times. Oops, I just realized this is not on the screen. So imagine that I did this, push 5, push 10, push 9. What would this mean? Now, as a linked list, okay, so here's my, what I'm doing is I'm going to push the 5 into my linked list. Now, at the beginning, this is what I would get. Okay, don't worry about things like Sentinel nodes. Those are implementational details, right? So this is what push front will do to my linked list. Now, if I then push the number 10 to the front, okay, if I do push 10, and remember, push is adding a number in front, okay? So what would happen is that the new node for 10 is going to go in front of the node for 5, okay? So what that means is that my front node is now 10, my back node is now 5. This is the newest item, okay? This is the most recently added item. This is the oldest item in the stack. So as I'm pushing data in, because I'm choosing to do push front, the newest item will always be at the front of the linked list. So push again, pushing 9 would add the 9 to the front here. Now, of course, what that would mean is that when I'm doing, as I add more and more items, the items that I'm adding always end up at the front of the linked list. So the newest item is at the very front. The second newest item is the second one, and so on. So the newest item here is 9. The second newest is 10. The next one is 5. So that's why we always pop front, okay? Because I chose to push front. Now, if I chose to push back, then it would be reversed because the newest item would end up at the back of the linked list. And when I pop back, that's where the newest item will be. So it doesn't matter in a doubly linked list whether you choose push front or pop front, push front or push back for your push, but it has an effect on the rest of your code. So once you have made this choice, you have also at the same moment made the choice of how you will implement everything else. It's not a mix and match. It is you are choosing the entire set, if you will. Okay. Once you've chosen push front, the pop function is definitely pop front because otherwise it's not a stack. Once you've chosen push front, where is the newest item? Where's the top of the stack? Well, remember, we're doing this in 5, 10, 9. The top item is wherever 9 is, which is at the front of the linked list. So the good thing about doing it this way is that it's slightly easier for this. This is simply returning star the stack dot begin. Because the newest item is at the front of the stack, begin, actually cbegin, because this is a const reference, cbegin will return an iterator to the first item, the first piece of data, which is 9, and that's it. This is and then access it. So this is going to give me the first item in the linked list. Okay. Now, again, you've already written this function. You can simply use it. And if this was a Sentinel linked list, this code will still be the same. It's not different for Sentinel, okay? Just because there's a Sentinel node doesn't mean any of the usage is different. So being able to use something that you've already created, that's pretty cool, okay? You don't have to rewrite your code to sort of be able to write a linked list. Your code is already there. Now, how about is empty? How do I know if a linked list is empty or not? Well, our linked list has push, pop, and then all the iterators. Push, pop, begin, end, and then a whole bunch of iterators. So how do I know if something is at the beginning? Well, it turns out there's a very simple check you can do. Simply return cBegin. Actually, it's the stack.cBegin equivalent to the stack.cEnd. If this statement is true, the only time this statement is true is when the list is empty. If the first item happens to also be one past the last item, then it means that your list is empty. This is the only time when this will be true, so this is all you need to do. Okay? Now, if you have chosen push back for the first one, what would happen? So if instead of writing push front, you had said the stack dot push back, then how would the rest of your code be affected? Well, it would be affected by this in the same manner. If you push back, your newest item is at the back of the linked list. So your pop has to happen at the back of the linked list. Similarly, the item that is at the top of the stack is also at the back of the linked list. Now, you don't have an easy way to access the last item. You have an easy access to the item after the last item. So this would end up being return star minus the stack dot cEnd. So if you take the thing after the last item, decrement it, and then dereference it, you would get the last item. So the code in the comments is what if you had written this one differently. Now, in a doubly linked list, you do have the option, the runtime for push front, push back, pop back, they are all O1. So there's no real difference in runtime between version 1, which is the better version in my opinion, versus version 2. Mostly because I don't like this. I don't like the way that you have to write top if you use push front, or push back, I should say, sorry. I don't like this particular, this construct. I think this is really awkward. So I do prefer push front because I think this is awkward. And if you choose push back, this is the only way. So there's different ways for you to do this implementation, but I think that this is a cleaner implementation if you use push front. Now, that's just a matter of sort of preference. If you have a singly linked list, what I just said isn't true. You actually don't have a real option. And the reason is because if this was a singly linked list, then what would happen is when you actually you only have one pointer to the last you only have a next pointer in each node. You still have a back pointer, but you only have one pointer to the next node and no pointer to the previous. So imagine what you would have to do if you were pushing, if you had chosen pop back. So let's say that I had chosen to do this with push back and pop back, so version B. What if it was a singly linked list? So here's some data. And let's say that I now try to do a pop, okay? So if I push, I'm going to put it at the back of the linked list. So push 11. Well, putting the number in is pretty easy. I make a new node. I make back arrow next, point to the new node, and then I point the back pointer to the new node. That part is fast, okay? Now, what would happen if I did a pop though? Unfortunately, if I tried to do a pop, I would also have to do a pop back because this is the newest one. This is the thing that I just added. I would have to do a pop back. And if I have to do a pop back, not only must I erase this node, that part is a given, I also have to take this pointer in the 10 and set it to a null. Unfortunately, the only way to get access to this pointer is to go through each of these and iterate until I get to the thing that pointed to the 11. And then I can then I can make this pointer a null. Unless I do that, I cannot. And that process, unfortunately, is expensive because I have to go through every single node to do it. So if this was a singly linked list, I would only be able to push front because popping back is slow. If I push back, I have to pop back. So if I'm choosing to implement this using a singly linked list, I would have to push front and I would have to pop front. Okay. So this is how you would implement a stack using a linked list. That's everything. Thanks.